All right, welcome. For any of you who are engineering and operating Spark at scale, you already know that performance, well, it's not just about your code's logic, is it? It's really about architecture. So today, we're going to go way beyond those surface-level configs. We're going to do a deep architectural review of Spark's memory management framework. Think of this as a technical deep dive designed specifically for senior engineers. So here's the roadmap for our session. We're going to start at the top with the high-level memory hierarchy. Then we'll drill down into the nitty-gritty of a single executor. From there, we'll explore the dynamic, unified memory manager, check out the incredible bare metal optimizations from Project Tungsten, see how it all plays with the JVM garbage collector, and then, this is the best part, we'll wrap it all up into an actionable set of tuning levers you can actually use.
You know, to really get Spark's memory design, you have to appreciate a little bit of its history. That big paradigm shift from disk-based systems like MapReduce to in-memory computing, it was absolutely revolutionary. But it also meant the primary performance bottleneck completely shifted. It moved away from slow disk and network I/O and landed squarely on CPU and memory efficiency. Spark's entire memory architecture is a direct answer to that shift.
So when you're thinking about Spark memory, you can't just think about one thing. It's not a single layer problem. At the very top, you've got your cluster manager. Could be Kubernetes, could be Yarn, and it's allocating a container. Okay, inside that container, you've got a Java virtual machine, the JVM, with its own heap and its own garbage collection rules. And then inside that, you finally have Spark's own highly specialized memory manager. An issue in any one of these layers can create ripples through the entire stack, so having this holistic view, it's absolutely critical. Okay, so with that high-level context in mind, let's deconstruct the memory of a single Spark executor. The executor, as you know, is the fundamental unit of work in Spark. It's just a dedicated JVM process that runs on a worker node. And I'm telling you, understanding its internal memory layout is the key to debugging almost any performance issue you'll ever run into. Right off the bat, here's the first common misconception: what the spark.executor.memory setting actually controls. A lot of people think it sets the total container size, but it doesn't. It only sets the size of the JVM heap. The total memory that you actually request from the cluster manager is the sum of this heap plus a supercritical non-JVM buffer called memory overhead and, of course, any off-heap memory you might have explicitly configured. Now, let's zoom in on the JVM heap itself, because it's not just one big block of memory. It's actually carved up into three really distinct regions. There's a small, fixed, reserved memory space, a user memory region for your own code's objects, and then the main event, the unified memory pool, which is where Spark does pretty much all of its heavy lifting. So let's break this down. Reserved memory? That's a hard-coded 300 megabytes for Spark's internal stuff. Simple. The rest of the heap, which we call usable memory, gets split by the spark.memory.fraction setting. By default, 60% of that goes to the Spark memory pool. This is for your shuffles, your joins, your caching. The other 40% becomes user memory. Now, this area is kind of the Wild West. It's where your UDFs and custom data structures go to live, and if your code is inefficient, this is where out-of-memory errors are born, because Spark has zero control over what happens here.
Now let's talk about that crucial slice of memory that lives outside the JVM heap: memory overhead. This is not for your Spark data. It's for everything else the container needs to just function. We're talking about VM overhead, native libraries, intern strings, network buffers for shuffle services, you name it. The default of 10% is often not nearly enough, especially if you're using PySpark or running in containers. Under-allocating this is probably one of the most common reasons containers get killed by the cluster manager.
Let's make this really concrete. Say we have a typical 12 gigabyte executor. The very first thing we do is subtract that 300 megabytes of hard-coded reserved memory. That gives us our usable memory space, which is the actual total heap that Spark's memory manager gets to play with. Next, we apply that default spark.memory fraction of 0.6, and we split that usable space. So 60%, which is about 7.2 gigabytes, gets allocated to the unified memory pool for Spark's managed execution and storage. The other 40%, about 4.8 gigs, becomes that user memory region we just talked about. Okay, so let's really focus on that unified memory region. This is, without a doubt, the heart of Spark's modern memory management. It was introduced back in Spark 1.6, and it replaced a much older, more rigid model. The whole thing is based on this beautiful concept called dynamic occupancy. Before version 1.6, Spark used what was called a static memory manager, and it had this hard, immovable wall between execution memory and storage memory. It was just incredibly inefficient.
You could have a shuffle-heavy job that was spilling to disk because it ran out of execution memory, all while the storage region was sitting there completely empty. The unified model completely solves this by creating a single, shared pool where execution and storage can dynamically borrow from each other.
Now, this is the single most important rule that governs the Unified Memory Manager. If you remember one thing, remember this. It's an asymmetrical relationship, and it's designed to prioritize one thing above everything else: finishing the job. Active computations happening in execution memory are considered sacred. They cannot be touched. But cache data in storage, well, that's disposable. It can always be recomputed later if it has to be.
In this slide shows those rules of dynamic borrowing in action. It's pretty straightforward. If an execution task needs memory, it can take any free space it finds in the storage region. If storage is full of cached data, execution has the authority to just kick those blocks out, using a least recently used policy to make room for itself. Now, storage can borrow from execution, but only if that space is totally free. It has absolutely no power to kick out active computations. This design ensures that your tasks don't fail, even if it comes at the cost of your cache.
So we've covered how a Spark allocates its memory. Now let's look at how it makes that memory incredibly efficient. And that was the entire goal of Project Tungsten, to bypass the inherent limitations of the JVM and push Spark's performance closer and closer to bare metal speed.
To understand why Tungsten was even necessary, just look at a standard Java object. A simple 4-byte integer, when you wrap it in a java.lang.integer object, can suddenly take up 16 or even more bytes of memory. That's because of object headers, metadata, memory alignment padding, you name it. For big data processing, that kind of overhead is just catastrophic.
Tungsten's solution is brilliant in its simplicity. Just get rid of the object entirely. By using a custom binary format called unsafe row, it operates directly on raw bytes in these nice, contiguous memory blocks. It completely eliminates all of that Java object overhead. It's really a fundamental shift away from object-oriented processing and toward direct memory manipulation. And Tungsten pulls this off through several key features. Unsafe row gives us that compact binary format. Off-heap management lets Spark store this data outside the JVM heap, which means we avoid those pesky garbage collection pauses. Whole stage code generation actually compiles entire query plans into optimized bytecode on the fly, getting rid of tons of virtual function calls. And finally, it uses cache-aware algorithms to make sure data fits neatly within modern CPU caches, which minimizes those expensive trips to main memory.
Okay, let's connect Spark's advanced memory model back to its host environment, the JVM. Because no matter how clever Tungsten is, at the end of the day, Spark is still a Java application. And the garbage collector can become a major performance bottleneck if you don't manage it correctly. It can cause these long, stop-the-world pauses that can seriously destabilize your entire cluster.
For Spark, there are really only 3 collectors you need to worry about. There's Parallel GC, which is optimized for throughput but can have really long pauses, so it's only good for smaller heaps. Then there's G1GC, the garbage first collector. It's the default in modern JDKs, and honestly, it's the best choice for nearly all Spark workloads that have heaps over 8 GB because its pause times are so much more predictable. And for those truly massive heaps, like hundreds of gigs, ZGC offers ultra-low latency, but you pay for it with higher CPU overhead.
So, how do we actually apply all of this deep architectural knowledge in a real production environment? Let's synthesize everything we've covered into a simple, actionable checklist of the most critical performance levers an engineer can pull.
First up, right-size your executors. You want to avoid those massive executors because they lead to long GC pauses. Usually, 16 to 32 gigs is the sweet spot. Second, increase your memory overhead beyond the default, especially on Kubernetes or Yarn. It's a huge factor for stability. Third, explicitly enable G1GC for any heap that's larger than 8 gigs. Just do it. Fourth, you have to monitor for spills in the Spark UI. A disk spill is a direct, screaming signal that your execution memory is too low. And fifth, leverage adaptive query execution, or AQE. It allows Spark to dynamically re-optimize query plans at runtime, which can mitigate all sorts of issues caused by data skew or bad initial partitions.
We'll end with a final thought, just to test this new mental model. So imagine your job is spilling heavily to disk. You pop open the Spark UI and you confirm it. Based on everything we just went through, which specific granular memory region is your absolute prime suspect? If the answer, execution memory within the unified memory pool, immediately popped into your head, then you've absolutely grasped the core of this architecture. Thanks for tuning in.